All right, all you.
Cool. Actually, give me 1 second here. Awesome. Okay, welcome everybody. So I want to talk today about some more conversations about system identification. I want to pick up where we left off talking about linear models a few weeks ago and bridge the gap from those linear models of linear dynamical systems to neural network models. So I think there's a lot to know, like a lot of practical things to know about neural networks, using neural networks for learning models of robots like this that we care about. But I actually think there's such a beautiful parallel between what we can see in the linear dynamical systems case and what we can see in the neural network case. And if I land one thing today, I want to land for you that parallel and make sure that you can think, I think we can think very cleanly and clearly about the linear dynamical systems case. And I hope it will help us think about the much more complicated neural networks case. So let me sort of draw a quick sort of outline, if you will, of what the biggest message I want to get across today is, okay? So if I talk about linear models over here, and then neural network models over here, then there's a few key cases that we've talked about, and I will finish talking about, I guess, here. So the first case is when we have state observations. Okay, so we have data that comes in the form, we have U0, but we also have X0, U1, X1, so on and so forth. Then when we're doing the linear models, we talked actually a lot about that case. We want the natural model to fit. For a linear dynamical system, is just AXN plus BUN, possibly plus W. We talked a lot about that more recently, okay? And the great thing about that was that we can use linear, because we have state direct observations of X and U, this just becomes a least squares problem, a linear least squares problem. And we talked about hydrodynamic cart poles and putting Legos on sort of assembling Legos and other places where you could make local linear models of pretty complicated systems. And that was a very, very powerful tool if we assumed that we had the state. There's a natural correlate for if you have the state, what you do with a neural model, right? So you can certainly learn a neural network model, just even a feed-forward network. That just predicts xn plus 1 is just some complicated function, the neural network, right, of xn and un, where these are the weights of the neural network, right? And that can be a multi-layer perceptron, for instance, is a standard thing to use in just this simple case. Oftentimes in robotics, people are using for this just a handful of a 256 wide hidden layer, maybe 2 or 3 of them, ReLU network, not a deep network. I would say they're relatively shallow, small feed-forward networks. Okay, and this becomes a nonlinear least squares problem. And we'll talk through the ways those are the same and different. Okay, but first let me stay at the high level. The second major case would be if our data is coming from IO data, meaning we have observations we have the command we sent, and then the observations Y, but they might not be independently. Any one Y might not be a full snapshot of the state. It might take, you might have partial observations. You might only measure the position of the cart, and you need to estimate the position and velocity to have the full state, for instance, right? And I'll show a couple, I hope, compelling examples of that here. Okay. Now, there's a couple types of models you can learn with this. In the linear dynamical systems case, we talk about a state space model, which is the natural extension from what we did before, where now we're going to still try to find some X, even though it's not available for us directly in the data. We're going to try to recover some X so that we can fit a model that we know and love. Possibly plus some measurement noise too. Okay, so if we have to find A, B, C, and D, right, in order to fit this model, that is equivalent to deciding what the state representation has to be, right? You could pick, you have to decide by choosing A, B, and C, for instance, what is even the right state to somehow summarize the input-output data I've received. And we'll talk a little bit more about that, okay? But what I want is to see that there's a direct analogy between that and then using in the neural network case, a recurrent neural network. For instance, using LSTMs, long short-term memory, and we played with the LSTM even early on, like lecture 2 or something, right, where we were playing with the pendulum and we were talking about nonlinear dynamics, and we drew the phase portrait of the LSTM as just another sort of interesting nonlinear unit that has some state to it. It's actually not my favorite, right? I think it's kind of crazy that people use LSTMs, but that's the one that everybody seems to use and seems to work quite well. Okay, and the model of this now is still a dynamical systems model, where it's the equations of the state space recurrence are given by the LSTM equations, right? And we really do have a system that takes UN in and has my recurrent neural network in the middle and spits out YN. And we can train this similar. It's still a nonlinear least squares problem, but we end up having to do a slightly different way to train it. Okay, and it's analogous and important to make the connections and point out the differences, I think, to the linear version. And then there's one last version which I think is importantly different than those two, which is the ARX models, which is autoregressive. The X stands for with exogenous input, which is just the, because we have a U, okay, but the autoregressive models, okay? So this would be, you can think of it as very similar to the state space models, but there's a couple, I think, notable differences. I'll write it like this. So I can choose to write Y as just a linear combination of the recent observations and the recent actions. Okay, and that's some finite list, some finite set of history there. And similarly, you will often see people using feed-forward networks, just multi-layer perceptrons or whatever, that have a history of U's coming in, but also a history of Y's coming in. Into, for instance, a multi-layer perceptron, right? and then just try to predict the next y. So I think a lot of people are very quickly just say, well, I can just use the last few observations, the last few images, if you will. In a lot of robotics tasks, we like to go from pixels to torques nowadays, right? Or in this case, since we're learning the model, they would be going from torques to pixels. And you could say, well, I can predict the next pixels just based on a short history of the images that I've seen, right? And that I'll just use the image as my state, is the kind of thing that people will say. And I think that is, of course, that can be rigorously correct. It can be wrong, depends on the setting, okay? But it has implications, which I think are super clear in the linear systems case, and they transfer over to the nonlinear case, okay? So this is the sort of map I'd like you to have in your head here, is that there really are kind of three cases. They're all related, of course, but there's a direct connection between the linear least squares we talked about with state observations and the feed-forward network case. There's a direct connection between the state space models from input-output data and the recurrent network case, where the recurrent units have their own internal state, like this first equation. And then the autoregressive models and the autoregressive case for a neural network.
Russ, can I ask one question?
Anytime, yeah, of course.
So you said the feed-forward network takes in the input as the history of inputs and the outputs. And my question is, isn't it also possible for the RNNs to do that, like inputting the history of like inputs and outputs? Like, why would you use feed-forward networks over like recurrent neural network when you still be able to do the same thing?
Of course, you can mix and match. I mean, then it's a little, it's not wrong to do that, but it's a little, you're somehow combining two different ideas, and they can be combined. You have to think about you know, why would you do that? What benefit would you get from doing that? There might be an interesting case where you could get some benefit from doing that. But the way to think about the recurrent networks or the linear state space models is that xn, if you've chosen it well, is a sufficient statistic which summarizes all of your previous observations and actions, right? It's a state, the definition of a state is it's the thing you need to know to summarize all of your history in order to make future predictions.
Then, like, you mean that it sounds like the system is fully observable in that case, I think?
Nope. So even in the okay, I understand why you say that, because in general you need the full belief. For planning, you need a full belief, right? But the state space, if you know the state, then you can make full predictions, even in a partially observable setting. The problem is, since the reason I think that you're making that connection is because if you don't know the state exactly, if nobody tells you the state, then you have to carry a distribution over possible states.
Oh, I see.
In the setting here where I'm making a model, it is true that if I were to know X, if I have X, I predict forward, X tells me everything I need to know.
Gotcha. Thank you.
Cool. Yeah, so if you, I mean, there could be a setting where you try to capture some part of your history with an X very efficiently, and some part with just a recent summary of a few of your observations. And there might be a setting where that works well, but it is mixing two ideas. Okay, so let's dive in a little bit more. So you remember when I talked about this, the state observations case last time, we did the sort of hydrodynamic cart pole, we did the Lego manipulation, and we wrote out that it was least squares. I don't think I need to say that again, but one thing I do want to remind you about is the difference between, because it comes up and becomes even more important, I think, in the network case, is the difference between the equation error and the simulation error. So let me just, I know you remember that, but let me just write it for completeness here. So if I'm given data of the form U0, X0, un xn, right? There's two different loss functions we talked about possibly using, right? So one of them was the equation error, which was just at all of my data points, I'm just going to predict the one step. So I'm going to minimize over alpha. I'll just write this for the neural network case now, right? Because we still have the same choice. So if I minimize over alpha, my prediction compared to what I actually got, the next step, that's my equation error, right? This is the case which for linear dynamical systems, LDS, I got linear least squares. And if I've got a neural network here, now it's just a nonlinear least squares. And it's like fully in the domain of exactly what we do all the time in supervised learning, right? This is a very standard supervised learning setup. So it's a very appealing in that sense. It's a case where we think it should work quite well. Right, the hazard with doing that though, is that you can actually minimize this error. You can get a very small equation error, residual basically. You've taken your loss down to very close to zero. And when you start simulating your neural network and you simulate, if you were to then separate and you were to roll out the neural network versus rolling out the true robot, then those trajectories can still diverge. Okay, this is a common hazard, right, of just doing the one-step error. Multi-step predictions can diverge. Now, in the linear dynamical systems case, you can do things like you can still do the one-step error, but you can add things like stability constraints to guarantee that you won't have this exponential divergence over time. I mean, basically, linear systems are either going to converge or they're going to diverge, right? And if you put some constraints on there, you can continue to use the one step and avoid some of these pitfalls. But since you can't really do that with the neural network case, we don't have the same tools for writing constraints on that the neural network would describe a stable system. People are working on that problem, but in general, I think we say we can't do that yet. That means that this hazard is even more relevant for neural networks. As a result, I've got a notebook that I'll push tonight of just even identifying the cartpool. And if you're not careful, doing the one-step error and you start rolling things out and the trajectories will diverge, even though the cartpool is a small problem and I sampled it pretty densely and the equation error goes down pretty low, you still see those things can diverge, right? So more common when you get to the neural network case is that people will optimize the simulation error, which I wrote before. I'm going to still minimize over alpha, but now I'm going to do the result sum over n. The result, let me write it this way. The difference between my data and my simulation, roughly, where the simulation is defined as the rollout under that model, using the data as my input. And the simulation and the data are only linked in state at the initial condition. Right, so the data enters here and here and here. But I'm going to roll forward from just the initial state and compare it to my true data. Okay, so this is still just a nonlinear least squares problem. but it's slightly different than the cookbook supervised learning problem, because there's this extra structure, okay, of having the same function looped over and over again, right? You can think of it, in fact, that is kind of the way people do it, is you can think of this as just a big network where you take the function f and you just apply it one after another, and then you do backpropagation all the way through it, okay? And it's just the fact that the network is copied over and over again adds this extra structure. But the standard approach to solving this, you'll hear is just backpropagation through time. Okay, so that's the way you compute the gradients of the loss in order to do efficient gradient descent, is by doing backpropagation through time. But I want you to know, I want you to be like screaming inside your head right now saying, wait a second, isn't that just a trajectory optimization problem, right? And it is, it's completely just a trajectory optimization problem. It's the same thing we've talked about a bunch of times. Maybe the only thing slightly different about it is that it's an unconstrained trajectory optimization problem, or only equality constraints is the way I've written it right now, okay? And in fact, the gradients of that trajectory optimization problem, the same equations, if you want to find the backprop through time equations, you can go to our trajectory optimization chapter in the text, because they're exactly the same equations. Backprop through time is synonymous with the adjoint methods from trajectory optimization. People in machine learning talk about it being independently rediscovered.
Isn't this a little different though, because the parameters we're looking for are the model parameters, not the trajectory?
Oh, good. Yeah. So you can do that. I mean, so we did it a couple different ways, but yeah, you think about taking one more derivative here potentially. So if we were computing the gradient of the cost with respect to u at time 3, for instance, right? We would do that by going backwards through time and taking the gradient with respect to u3, okay? And it's just one, if u3 is a function of my model, then it's like one more term in the chain rule. But the key step is that just like in backprop through time, you can do sort of chain rule calculations forward in time and carry a big auto diff gradient. It's the difference between forward differentiation and backwards differentiation, if you know anything about auto differentiation, right? But the key insight, I think, that makes both of them work is this adjoint method, this backprop through time, which is that you can just carry the gradient of the current layer, current state, the gradient of your loss with respect to the current layer, and that's the only thing you have to go backwards through time. And the optimal control people call that the adjoint equation, and the neural network people call that the backprop through time. And if you carry that partial, or it's also a Hamiltonian, if you like the Hamiltonian version, right? But if you carry that one gradient backwards through time, then you can spin off and take the gradients with respect to your parameters, or the gradient with respect to your control input, or whatever that is, as a function of that long-term derivative. Okay, there's two other points I think to make about even the state-based neural network case. Two more, The first one is, how do you generate the data? Okay. So in the linear case, or even in the multi-body parameter estimation case, let's take the multi-body parameter estimation case first. If you'll remember, we assembled this big data matrix with the lumped parameters, and we used the condition number of the data matrix as our objective for designing parametrically exciting trajectories. Roughly, we could write a trajectory optimization that says, I don't know what the values I'm going to get in that matrix are yet because I don't know the system, but I can design input trajectories that will give me increase the condition number of that matrix. Okay, and that's a very nice idea. It kind of gives you a sense of how to do the exploration in order to get good data for system identification. Okay, and that's leveraging the fact that we're doing linear least squares. Okay, the same kind of thing happens in linear system identification because we again are using linear least squares, and you can talk about trying to optimize the condition number of your data matrix, the Hankel matrix it becomes, for instance. Okay, but even in the linear case, it's even somehow easier. To the extreme, if you have no noise, then you can even just do an impulse response and know you've done, if you do enough impulse responses, you've got all the data you ever need, and then you're just driving your noise down. So it's a potentially easier problem but still a good problem in the linear dynamical systems. And when you go to not fully nonlinear least squares, those tools are lost. I mean, you can make approximations of them, but we don't have the same notion of what it means to be to generate the right data. Well, we don't have as simple of an explanation of how do we generate the right data. There's a lot of good work happening now in the model-based RL community that has been thinking a lot about this, especially some of the people thinking about offline or batch RL think a lot about the importance of the distribution over your data compared to the ultimate performance. Okay, so I won't give those results here, but I did sprinkle a couple pointers in the notes if you're interested. Just to say that I think the big intuition to have, and it's one of the reasons I wanted to wait till we had done some more stochastic dynamics. Okay, so if you have a nominal controller and you have some dynamical system, then we understand now how to think about a distribution moving through that system. Okay, and we talk about how the distribution can converge to a stationary distribution in some good cases where you have stability, right? And we have these notions now that we've built up for stochastic dynamics. So the data that you would like to have for system identification in the fully nonlinear setting is you'd really like to be pulling effectively from the distribution induced by the optimal policy, right? What you'd like to do is you'd have your data represent the data that you would get once you've got your model and you're executing the optimal policy. Now, there's a clear chicken and the egg problem with that, right? Is that you can't build your controller to build the until you have the model. You can't even. So there's a chicken and the egg problem with that. But I think a lot of the online and model-based kind of ideas are talking about right ways to sample from this distribution. And I think the biggest lesson probably is that maybe we have to give up on this idealistic notion of fit a model once, done, period, fit a controller, and think more about the interleaving of designing the controller and the model, right? And expect your model to be accurate in the places where you've got data. And as you change your control law, the places where you need data has moved. And so you need to get new data and fit a new model. And ultimately, you may never cover the entire state space, but you need to cover the parts that you're going to live in. If you think about blowing that up, I mean, to the whole complexity, I kind of joked about this early in class, right? So I'm a humanoid. I've got lots of degrees of freedom. I haven't had enough time in my life to visit all of my states, right? I probably don't have models of a bunch of weird configurations of my body that I've never visited, right? But I don't need them. What I need is the reasonable models of my dynamics in the states that I visit often, right? And then maybe some robustness and some common sense, so I don't put myself in those configurations in the first place. Okay, so that's one really important difference about just how do you generate the data. Like when I was coding it up this morning, I was just, I was like, okay, cart pull. I'm thinking, what's the best simple example way to generate the data? And there's really not a one right answer, right? I started generating sweeps and whatever, and it's, in particular for an underactuated system, it's kind of like, it emphasizes this point, right? Because if you just send in random inputs to a cart pull, it's never going to visit the upright configuration, right? But you really ultimately want data around the upright configuration. So how do you get that data when you haven't yet built your controller? So I think, even though they're very simple toy models, they can capture some of those harder issues. Okay, the other one that I think is worth calling out is a lot of times when people do model-based RL as MPC, model predictive control, right? Is let's just say it's odd, strange. It's not in some like mathematical symmetry argument. It's just different from how we've done it. How about it tends to be different. I don't know that this is a long-term thing or this is like a short-term thing that the field's kind of caught in it hasn't quite figured out the right way to do it. But people tend to use, you will not see SNOPed, for instance, right? In the MPC loop, you'll see CEM, cross entropy methods, and you'll see MPPI, which is this, let me write it down here. So IP-opt is another one that's in that family. A lot of people use for mechanical model based, like walking robot people and stuff. They use SNOP, they use IP-opt, right? But neural network things, you tend to see CEM, cross entropy method. Write it out. Or MPPI, which is they're very similar. Basically, people have written papers about how they're similar. It's the model predictive path integral. The details of those algorithms, I can leave it as a link for you, but they are the key point is that these are zero order optimizations, gradient-free optimizations. Whereas SNOPed is first order. So they will tend to, for instance, just run lots of simulations, not take the gradient, but use the batch of simulations to make, well, in the cross entropy, you make local Gaussian approximations, you estimate the covariance, and you make an update based on these sort of covariant estimates, okay? So this one's funny, and I'm actually curious if people have any thoughts or opinions about this. I've asked a lot of people why this is. Anecdotally, it seems to be very consistent across the field. We've seen it in some of the work we've done where these tend to perform better. But for all so many people talk about, oh yeah, let's make a model differentiable by putting it in a neural network, but then they don't use the gradients when they're doing planning. So that's pretty weird. So let me say my two hypotheses, and from the people I've asked and the students that have taught me what they think, and then you tell me if you have any others. But I think there's possibly two explanations. One, I think, is that the model can fit your data very well, but the gradients can be sort of locally noisy, okay? So, you know, if I have a bunch of data like this, you know, I'd love to get a beautiful, smooth function that goes through it or whatever. But it might be if I zoom in here, then what it'll actually kind of like a little bit, you know, we made them out of rectified linear units. And it might be that a purely gradient-based approach has trouble with those kind of little kinks in the optimization landscape. I think that is a reasonable hypothesis. It's one I think deserves more exploring. I think some people have looked at it, I'm sure, but I've never looked at it myself enough to be convinced if this is the problem. But it's a reasonable thing. The other reason is that basically the GPU makes massive parallelization cheap. Parallelization cheap. So zero order methods start to compete with gradient methods because of the parallelization. But in general, if you just, by most metrics in terms of like how many simulations, how much are you going to raise the temperature of the room by computing, you know, one of these methods versus the other when you're doing your optimization, you would expect the first order methods to converge more quickly and with less samples than a zero order method. So, so I think from my perspective, it's surprising that people aren't leaning more heavily on gradient-based methods based on having a differentiable model, you know, in a neural network. But in practice, I see that they're not. Anybody have your own hypotheses?
I guess I have a question, and then also an agreement with one of them. Did some work in like Grady's lab, the group that came out with MPPI, and that second explanation seemed really appealing. Like there's a large kind of draw to how do we parallel, because you're kind of shooting out a lot of trajectories, and you can evaluate them in parallel. There's no reason to make this. I was running a mathematical program last night with Drake. Is this acceleratable with a GPU?
Yeah, totally.
And so like the first one sounds really cool now that I hear it. Now is like another explanation that should be studied, but like the second one from personal experience seems to line up, that you can just kind of stick a GPU on your platform and tell it to go.
Nice. That's super good. Yeah, you said you were working with Byron, or were you working with?
I was working with Byron, but I did some work with like Grady Williams, and that's like Theodora's group.
That's awesome. Okay, first.
I had to sit and build one of their cars for them and get you in there.
Awesome, first-hand experience. So yeah, so they're the authors of the MPPI algorithm that I've written here. So great to have your experience here. That's awesome.
So yeah, and then on the other hand, so I guess this was kind of a question I had. With SNOPT and IPOPT, we're writing down a cost function, and then we write down a bunch of constraints, and we tell the solver to go find a solution that minimizes cost under some constraints. And is that a framework? I mean, like, I don't think when we do MPPI, we're like explicitly writing down like, here are some linear constraints I have, or here's some nonlinear constraints I have. I think I'm not sure if that's right, but
no, you're totally right. That's a great question. So typically, the zero. I mean, so even it's a little weird for me to call SNOPT a first order method because it's using first order derivatives to make a second order method, and you know, it's actually solving a QP. Okay, so let me be a little bit more careful and say first/second order method for SNOPT, because it only demands that you supply gradients, but it uses those gradients to make a local Hessian approximation. Right. So when you solve a QP on each iteration, that's like the generalization of doing the Newton's method sort of to find to do your descent, and you can include constraints in that, and that's very powerful. I believe, I have probably communicated ad nauseum that I believe that it's better to write constraints if you know that you have things that are constraints than to have lots of penalty terms that you have to tune on costs, okay? If you go to truly first order methods, just gradient descent, then you can try to do some constraints. You can do like projected gradient descent, where you'll take a gradient descent step and then project it back onto the feasible set. But it's harder in general. I think you're more limited in your ability to consume constraints, even in first order methods. 0th order methods, I agree with you. At most people, they will accept bounding box constraints, right?
Mm-hmm.
All is not lost, because I think increasingly, so although I don't like when people put things in the cost function and then tune their own penalties, I think tools like augmented Lagrangian, which basically are a recipe for moving your cost, your constraint into your cost, but then tuning the penalty on a schedule that we guarantee will converge at some rate, have taken some of the art and and tuning out of that. And if you really do want the constraints to be effectively hard constraints, and you are only able to use NPPI or some other 0 order method, then you can do it with things like augmented Lagrangian.
So I guess there's this trade-off between having the GPU acceleration or having your hard constraints.
I mean, for the same, we experienced it a bit when we were talking about iterative LQR, right? People use iterative LQR for problems like autonomous driving, where you do have some hard constraints, like you don't want to run into somebody, and they do it by shoving those things into the cost function. And if they're careful, they will use something like an augmented Lagrangian to try to drive that to a true constraint without making the problem. I mean, right? So the standard problem is, if you're not clever about how you tune the penalty you put on your constraint, then you will make the problem stiff to begin with, and then or insufficiently tight at the end. And so there really is a right schedule to tune up the magnitude of the cost you do on your constraint. Awesome. So let me go back to my outline here. So let's think about the IO data state space model version of this now. Okay, so I was trying to think of a cool example to bridge the gap, and I started playing with like, can I stabilize the cart pole from a camera? Okay, so that's going to be my working example here is for IO data state space model. Stabilize the cart pole, but with I forgot to I couldn't afford the encoder on the track or a joint sensor or whatever, so I just put a camera off to the side because somehow they're cheaper now from a camera. Okay, so let's just think about, I want to contrast the linear approach with the fully neural network approach. Okay, so is there any hope, if I've got a camera involved, of using a linear model, right? I think we can make a simple argument for why that's not going to go well for you, right? If you take your RGB inputs, okay, let me get a reasonable prop. I have a robot right there, but it's not very movable. So I got a Robo Apocalypse book. Okay, so right, so here's my pendulum on my cart pole, right? And if you're looking through this camera here, you're seeing at this place, at this pixel, you're seeing a red value, okay? But if I make an arbitrarily small, infinitesimally small change in the orientation, which is a change in the state, then that pixel discontinuously went from red to rust color, right? So there's kind of no hope. And I mean, you can get into the weeds in the differential rendering literature. They do talk about, possibly the dithering effect that you put between pixels can potentially give you a little bit of a gradient, right, to chase. Okay, but it really is pretty sharp discontinuity that this pixel, which if I say my my y is my pixel space, which is like, you know, this is y 232 or something, it's red. Epsilon change, now y 232 is rust color, then you know, then that's a good indication that linear models aren't going to work very well. But all is not lost. Neural networks are amazing, and so the thing that we've had a lot of experience or a lot of success with in my group over the last few years has been to train a neural network not to necessarily solve the whole dynamics modeling problem, but to just convert from RGB space into a more reasonable space. And this isn't a surprising idea anymore, but we can just get out. RGB pixel space is just bad. You know, don't live in pixel space unless you absolutely have to. Use something like a deep network to get you from pixel space into a more reasonable space. And there are good candidates for that. My favorite one is to actually do it into a geometric space, like using something like key points. And I'll let me see if I can show that example here. So if I say y of n is an RGB camera image, implies sad, y of n is for instance, I'll show you key points, then the linearization can work very well. So lots of people in lots of, oh, that's too bad. That'll come back. Well, it's just a bunch of chairs being flown around with key points, okay? But this is something that the computer vision community did independently of caring about robots or anything like this. As a pure computer vision problem, there are many cases where it's super interesting to go from an image or a sequence of images in tracking some key points, okay? So in the human pose estimation world, they will actually track like some nominal points on a skeleton, and they'll use those tracks to then reconstruct the skeleton. And there's like incredible videos of people dancing around and neural networks tracking the pose of these of the dancers perfectly. That was, you know, 6 years ago or something now. So those are amazingly good tools, and they can actually solve this fundamental problem of RGB space being bad, and moving this into a space like if I'm tracking the location of a handful of key points, then I can expect a linear model to work well. So let's think about that. Okay, so here's my cart pole. I put a few key points on the cart. It's hard to see when it's static, but I'm going to play the little animation and you'll see it. Okay, and I put 6 key points on the cart and 6 key points on the pole. Okay, so this is my cart pole training data. I just put it in the regime of a, like I did before. I took a controller using sort of the wrong model, but I stabilized with the wrong model was okay enough that I could stabilize and generate data around the fixed point, the balancing fixed point. But I'd like to learn a model that's somehow better, okay? But instead of doing it from state observations, I want to do it from key point observations. Is that cool? Yeah? Okay, so so how do we do that? So maybe I don't have as much time as I might have left for you know, for the linear dynamical systems approach. I can do this input-output state space identification with basically the Ho-Kalman algorithm, which I've tried to write up in your notes, okay? But roughly speaking, the idea, I can give you just the big idea here, is if I have some xn plus 1 axn plus bu plus noise if I like, yn if I start this off, then I know that y of 0 is just d of u 0, y of 1, I can roll out the response of the system to any input, okay? Y1 becomes, I mean, maybe it's also plus C of x0, okay? If I roll it out though, y of n, let me get it right. I can write it as this big matrix, C of a to the n minus 1, C to the n minus 2, all the way through to CB, D. It's a big block matrix, okay? Times the inputs I've passed in, which in this case would be staggered, just lined up like this, minus n plus 1 all the way down to un. And that completely describes what I would expect to get from a linear dynamical system that had, if I had a known A, B, C, and D. I can, my initial condition terms might come in separately, or anything that's more than my capital N history, okay? So ultimately, of course, if I want to get A, B, C, and D, then I've got a harder problem to solve. But on first pass, I mean, this big matrix here is nothing more than the impulse response of the linear system. It's also known as the Markov parameters. But the idea in fitting these state space models of linear dynamical systems, the standard idea is that you find these Markov parameters first. You solve just a least squares problem to find these matrices, not the individual matrices, but the sort of over parameterized, I'm going to fit each of these individually. And then it turns out, because D appears here by itself, you can easily extract D. Because C and B appear on the outside in this convenient way, you're not going to be too surprised to know that you just, with a little bit of singular value decomposition, you can actually break this apart and pull out C, A, and B. Okay. What I want you to understand is that there is a great algorithm for this. Okay. I mean, and people have even recently understood that it's good in terms of, you know, in finite samples, rejecting noise well. Sorry that they're mowing the lawn next door. Okay, so the basic approach to the state space realizations is you fit the impulse response with least squares, and then you extract A, B, C, and D with a singular value decomposition. A, B, C, and D are not actually unique, or well, A, B, and C in particular are not unique. We'd mentioned before the similarity transform, but the SVD picks one for you, basically. Picks a perfectly good one. Okay, so here's the big question I have for you, that I had for myself when I was writing up the code, right? So I've generated data of key points moving around on the screen from a cart pole system. I know the cart pole system has 4 states, right? I know there's a state space model that exists. It's a nonlinear state space model, not a linear one, okay? One of the amazing things about this approach with the singular value decomposition is that it can kind of tell you how many states you need to describe the data, okay? So you look, the states are ordered by the magnitude of their singular values, and you typically see a fairly rapid drop off where only the first few singular values, the components, you know, the states associated with those singular values describe most of your data. So by doing in this linear least squares regime, you can actually find out what is the state space of my system just from the data. Okay, so the big question I had was, if I run this on data generated of key points, is it going to realize that my carpole has 4 states? That would be awesome, right? Now, the reason it wouldn't work, I mean, I can add noise or not add noise. I forget which one I did in the plot I'm about to show, but the one, the reason it might not work is because it's a nonlinear system, even if I don't add any noise. If it added noise, again, I could have just, if it's a noisy data and I only have a finite amount of it, I could have somehow made that less perfect. Okay, so stop that. Hello. Okay, first off, it generates, there's an estimated and actual impulse response, just fitting from least squares. I could plot all of the key points, but I just plotted one of them. A lot of them look pretty similar, okay? And it looks like the impulse response, at least, has done a pretty good job of capturing the response, okay? Interestingly, when I did start plotting the impulse responses, I was mad at myself for not realizing a priori that I had basically, because I'm giving the X, Z, both the vertical and horizontal position of the key points, and the key points that are on the cart that go like this, the Z value never moves, right? So there's a whole bunch of impulse responses that are just completely 0, and I thought, oh, that was a waste of effort, but at least it told me that, and it didn't blow up, right? So there's a bunch of like non-information in the Z height of the cart key points. Okay, and then the thing that's interesting is if you plot the singular values, the magnitude of the singular values of the Hankel matrix, which is the data matrix. I think I've written it up fairly carefully, and the code is all there already. Then what you see, this is a log plot. What you see is that actually the first 2 states describe a lot of the data, okay? If you use 3 or 4 states, it looks like it kind of wants 5 states, and that must be the nonlinear thing. And then there's a pretty good drop off after that. So it really does kind of find out that there's 4 states hiding in my data, and that's awesome, right? I think that's just so good. It feels like it's found the essence of my problem. In the notebook, if you run it, you'll see that I just made a plot of the example where I linearized the carpole and then did the whole thing with generating data from the actual linear system, to test that hypothesis that it was the nonlinear terms that were causing this. So if I generated data from the actual linear system and ran this algorithm, that it really goes, singular value, the first 4 singular values, boom, and then it's like 1e to the minus 14. Like the magnitude of the singular values is just really gone. So it's good. I feel like that's a good example to bridge the gap. And it's a case where the linear systems can still describe a pretty complicated observation space, I would say, in the regime close to the balancing. Of course, if I go away from the balancing, then I expect this to get worse and worse because the dynamics are not linear. Any questions on that? So the optimization that it's solving here is in some sense a long-term optimization, right? And it happens in this step where I do a least squares over this whole, like rolled out data matrix, okay? In the neural network case, in the recurrent network case, we are again gonna do, use backprop through time. To train LSTMs. And There's lots of details in the LSTMs, but it's a similar idea, except for the state space equations are now parameterized by a small neural network effectively, and the thing that gets to that recurrent layer might be a small neural network, and the thing that leaves from that neural network back to the observations can be a neural network. So it's just a fully nonlinear version of this. But in that case, some of the magic is gone. So sorry, there's new magic, which is that you can fit crazy complicated different systems, okay? But the thing that's lost is this notion of, basically the SVD magic is lost, right? So there's really not a notion to my knowledge, of finding sort of the minimal realization of the system, or discovering how many states you need. You can of course try to fit your data with 4 LSTMs and 5 LSTMs and the like, but because it's a nonlinear optimization, it's harder to conclusively understand that you understand the performance with 4 LSTMs versus 5 LSTMs and the like. So I think it's worth exploring that and trying to walk that line. But you know, the SVD just saying, you know, these are the ones you need, these are the ones you don't need, that's just really good, and it's not available more generally. LSTMs tend to also be harder to work with in terms of planning and control, right? So again, people often will use, for instance, MPPI or CEM kind of methods to do the planning. And I don't, you know, we've done a little bit of work trying to understand if you can do sums of squares, for instance, on LSTMs. And I kind of know, I could tell you what I know about it. And maybe there's a future there, but when the networks get very big, it's hard to do structured optimization on them. Let me just show, some of you who were in the manipulation class saw this example before. Let me just show the example of where that has worked well for us. So first of all, it'll just be 2 slides of this. But first of all, that notion of key points, I think if you've thought about key points before, one of the first questions you might ask is, well, I don't want to have to sit there and do training, supervised learning of my key points in order to run this algorithm. And there is a lot of good work. This is just one example of sort of self-supervising your key point training. So you can really, in my mind, you can sort of just have the robot learn about the geometry in the system and effectively train itself to find some key points. Okay, that's a pipeline that works fairly well now. In some cases, there's harder cases, but for semi-rigid objects and the like, it actually works pretty well. So this the technology here is that you can track points between frames. So there's on the left, there's a mouse that's over one piece of the hat. In the middle and right images, there's a video playing, and it's trying to just tell me where is the same point on the hat. Okay, and this is a dense. You can think of it as dense key points, whereas I can put the mouse over any point on the hat, and it will try to tell me all of the similar places in the other image. Okay, so that's a tool that can be trained through self-supervision. So the robot just sort of, you know, moves itself around, or you have multiple cameras looking at the scene while the bits are moving themselves around. And just by saying, oh, this part that I know must be the same pixel, I saw it from this angle and I saw it from this angle, so therefore I should train a network to make those the same, and network endpoints that are not the same in that data should be different, is enough to sort of train these sort of front-end networks. So I really do think, and that the whole self-supervised pipeline is just getting better and better and better. I think many of you know a lot about it, but that is an exciting way. I really do think we don't have to deal with RGB space directly anymore. These kind of things bridge that gap. So this is for a simple manipulation task, an example of exactly what we were just saying, where it's extracting the key points on this sugar box in this case, and from a handful of pushing the box around, including the making contact and not making contact. We trained an LSTM network. Lucas trained an LSTM network to predict where the box was going to move. And then he used MPPI to do model predictive control. Boy, that's a lot of acronyms. Sorry. So yeah, you got it, right? LSTM, MPPI, MPC, or something like that. Okay, so and it worked, quite a bit better than our previous work in the sense that it required only just a single sort of, you could use one demonstration to do many tasks. That was very important to us. But although the key point detection and even the model learning worked for more complicated tasks, like putting the hat on the rack, like I just showed you, the planning was still a bottleneck for us. So well, and COVID happening exactly when he was trying to graduate. But, some combination of like, we don't know how to plan through LSTMs, and COVID limited our success on that. Okay. But I do think, I think that's a strong analogy. State space models, linear dynamical systems, key points, or LSTM models and neural networks. And the big difference is that the neural networks can represent almost anything, but we don't know how to plan in them. Okay. And the linear dynamical systems are super limited, but we can do super good control with it. So I'm still hoping for something in the middle. Okay, I know I want to try to say a few things about this last, it's not a quadrant, it's the last piece of my 6-up chart. Okay, so the ARX models, what would it look like if I just took a history of key points, for instance, and I learned a map from my my recent key points to predict my next key points? So first of all, I actually think that works fine. I think, sorry, at a conceptual level, I would expect that to work. We can type it in, okay? Because, yeah, for instance, if I have just 2 snapshots of my key points, then I know there's a function, if in the noise-free case, for instance, in just 2 sets of key points, I could extract the current position from the most recent key points. There's enough information just from one image to know the position of the cart, position of the pole. And from 2, I could get the velocities, right? And if I have more, then I could potentially have a filter that would give me a better and better estimate. So I certainly expect those to be sufficient. So why not use a model like that? I mean, we can, but what are the pros and cons of using a model like that? And first off, let me say what you're probably thinking, which is that, of course, I can go back and forth between these two. And if I have a finite history of y's, then you can really just take my y's and my u's and stack them up in a vector and say, oh, that's my state vector x, right? And then you could write it in the state space model form. So of course, there's a mapping back and forth between them. But in practice, there's a difference between trying to find some minimal realization of x versus just throw the whole kitchen sink of last observations in. And one of the big differences that brings up is that, for instance, if I use the key points, I might have to fit more A and B matrices, but I'm okay with that. That's just more matrices. But the system that I get out in that state space is not controllable, for instance, right? So let me just write here. I want to make this, I mean, this is a general property, but I need to be careful about saying it because there's a proper statement of this that I would need to make carefully, which is that, if there is a realization that that X has a controllable realization, right? And then it may not be, I mean, oftentimes if you add extra things into your state, superfluous information, then you might lose controllability. For instance, controllability in a state space that has my key points listed would require that I could independently move my key points, and I can't, right? I can only move them, you know, in a coupled way. In fact, the Z position of my key points on my cart, I can't do anything to move those. So clearly those aren't controllable. But even the ones that are moving around, they move together, and therefore the standard assumptions of controllability are broken. And if I did LQR on this, it would say no, you can't just stabilize that state space realization, right? So there are differences that happen here. So I think this is a powerful tool chain using histories of observations and histories of view, and the fact that that works. There's variants of it too, where you put local, like a local filter to summarize your histories. But just be mindful that it's inefficient in terms of a state space. And that inefficiency can actually hurt some of the control approaches if you're not careful. Okay, just one last point to make on that. Give myself some white space here. ARX versus the states, let's say, I'll call it the minimal state realization. I think the differences in the linear systems case, you can go back and forth, and we know everything sort of about the way those are related. But in the nonlinear systems case, there are times where a single state variable can capture a very long, some concept that has a lot of a long correlation in time. So let me say that better. So for instance, in partially observable settings, especially nonlinear settings, the state space can be much more efficient. So take as an example that, let's say I'm, people have used these kind of techniques to play Atari games, right? So there's a, pick your favorite Atari game, but I don't know, like Montezuma's Revenge is one of them, right? Where you're running around and you're, I had to remember what Montezuma's Revenge was, but you have to like go find the door, and then you go find the key somewhere else, and then you climb a ladder or whatever, you jump over some evil characters, and then you unlock the door, and maybe the red door and has the red key or something like this. So let's say I'm in a game where I either have the red key in my pocket or I don't. And then I'm running through my mazes and my levels and climbing stairs and whatever. The recent images don't tell me whether I have the red key or not. But if I just had one little state variable and I mark down, do I have the red key? Yes or no, right? Then I can remember that for a very long time. So if I were to try to build models only based on some history of observations to solve that game, then the history has to be long enough to remember any time I might have possibly picked up a red key and the duration of time between when I got the red key and I got to the red door, for instance, okay? Whereas a single little state variable could have done the same job, right? So I think those differences really can highlight when an LSTM approach can start beating an approach based on jamming the entire recent histories into your network.
Hey Russ, I have a question.
Yeah, of course.
So in the minimal state realization case, it seems like there's an underlying assumption that you have like a larger scope of data. So in the example that you gave of the cart poll with the key points, those were kind of capturing the cart poll in a global sense. So, I mean, yeah,
that's a good question. That's actually an incredibly good question, right? Because I think both of the ARX models and the state space models will, potentially only do well in the vicinity of the data that they've been trained. And if you think about this in a dimensionality argument, right, then, in a generalization argument based on dimensionality, for instance, then there's more possible Y histories, that I might have experienced or not experienced than if I'm able to summarize it in a smaller vector, then potentially with less data, I'm more likely to have covered my state space. Is that the point you were making, Bilkit?
yeah.
Cool. Okay, so just a couple other examples there. So there's this constant conversation that people have about, deep models versus physics-based models, and I think I would like to add linear dynamical systems models in the middle, but we know that linear dynamical systems models are going to suffer in describing the robots we care about. One thing I don't like is when people say deep or sort of physics-based versus data-driven, because I think both neural network models and multi-body models can be fit to data. So, but if we say deep models versus physics-based models, then I really think it's important to keep in mind the differences are potentially about the way that they're written down, right? So I think the state space models, if you can think about our Lagrangian mechanics models, our multi-body models, as being state space models. And they're a beautiful, efficient state space models, that describe sort of exactly the realization, the generalized coordinates, exactly the right nonlinear terms. When they work, they're the way to go. Recurrent neural networks, I think, fit in that state space model form, right? And feed-forward networks are often used nicely in this sort of ARX models. They are similar but different, and I want you to sort of understand those differences. Even the way you do synthesis on an ARX model is a bit different. Okay, so again, if you take away just a little bit from the conversation, right? I really think that the big challenges here are when I talk about like things that are hard to model, that are, I think Atlas, we kind of know how to model, but if we're starting to do manipulation and we're trying to do laundry folding or spreading peanut butter on toast or something, and we don't know the models, people say, well, physics-based models aren't going to get us there. And I say, hold on, I don't know if that's right. I think the problem with the physics-based models is actually that we don't know how to do state estimation, or we shouldn't have to estimate the full Lagrangian state, right? And that is, I fully admit that that's a big problem, and that's a hard problem. And describing every molecule of the peanut butter should not be necessary for the task, okay? Or describing the whole state of my shirt. But I think that the deep models haven't solved the problem yet either, because even though we can fit these models incredibly well to all this data, the generalization question that Bilkit was just asking about is still real, very real. And our ability to do planning and control design is still very limited when the model is trapped, if you will, in a deep network. So I think the work that's going on, in my group, for instance, and a lot of places, is trying to find some ground where we can have the power of representational power, the model fitting capabilities of a deep network, but the planning capabilities that are more familiar, that we're more used to having good planners for.
Just to push back on this though, like I feel like the best examples of planning we have are biological systems that don't use physics or like don't solve equations to do their planning. So I kind of like wonder what you think about that?
That's an awesome question. So, okay, so and it's at a good point. So a lot of so one thing that does seem to work okay is if you are able to learn a deep network forward model, and then you want to turn that into a policy by using RL type approaches, that has seen more success. Okay, so maybe animals. So animals do plan, right? Certainly, but a lot of their best stuff isn't what I think of when I think of planning, right? So, you can see crows getting worms out of a hole by making a stick and whatever. There's all kinds of great examples that we can find from biology. But when a bird is soaring over a cliff, and doing sort of beautiful little micro corrections in its feathers to stabilize its head, I don't think it's planning there as much. That's a subtle thing. And people, even the cognitive psychologists, I think, one of the working hypotheses is that maybe people have a small physics engine in their head that it might not be so different from a multi-body set of equations. We don't know, but the ability to parse things into objects, people seem to certainly have objectness. Even animals have objectness, right? And object permanence, and this notion of things don't move until they're touched, right? And a lot of things that maybe the data would describe, but they generalize pretty well, to the point where you kind of think you have a factored representation that looks a little bit like a physics engine. So yeah, it's in the fringe of what we know and can do, but I don't know that biology disproves this this feeling. Long answer for a short question. Did that address your thinking, Charles?
Yeah, I mean, I think about this sometimes too. I don't really have a good answer either.
Mm-hmm. Cool. Okay. Well, 1 week left, right? So keep asking questions if you have them. I see there's one that came in this afternoon. I'll try to get to soon. And okay, we have one more lecture, and then we have your videos. So I hope I was clear on the Piazza that I love it's really, really good to have these viewing sessions where we watch each other's projects. It's like you just learn so much about what works, what doesn't work. Russ said that worked, but actually nobody got it to work. So I learned something different there, right? It's very, very valuable to watch the other projects. If you want to be part of those projects, submit your video by noon that day. I will throw it in slides.com and we'll hang out and we will watch our videos. But technically your videos due by midnight with your paper, or if you have a reason to ask for an extension, you can ask for an extension. But the opt-in for video watching, video sharing is please get us your video by noon that Thursday. And ask us any questions, and I hope you'll opt in, of course. Cheers.